Hi, we're Team 3 and my name is Brooke, Willin, and my teammates are Raheel, Chaudhry, and Kevin Ward, and we are doing the analysis of a 4-bar mechanism as well as the synthesis of a slider crank. So to begin with an introduction of our mechanisms, a mechanism consists of links and joints which can vary from very simple and linear to involved with several degrees of freedom. Mechanisms designed with linkages are meant to take an input to produce an output that alters its motion, velocity, and acceleration. Two types of mechanisms include a 4-bar and a sliding crank mechanism. A 4-bar mechanism is a small link called a coupler that acts like a crank to drive usually two connected bars in a linear oscillating motion. Another movement consists of restricting the coupler so that it becomes both the driver and the follower link moving in a circle. On the other hand, a slider crank converts rotary motion into reciprocating linear sliding motion along a path. Starting as far back as the Roman Empire, slider cranks were used to aid in the water extraction process. Subsequently emerging into the time of the Renaissance, engineers tried to make sense of mechanics. With Leonardo da Vinci, he tried to explain and design several complex systems involving 4-bar and slider crank mechanisms. While he didn't know math, he did explain and demonstrate how to resolve lockups within 4-bar systems. And he also mentions that slider cranks are the most praiseworthy designs, yet he offers no immediate use for them. Moving into the Industrial Revolution, the concept of 4-bar and slider crank mechanisms boomed. From this point forward, the systems can be seen in typewriting, power conversion, piston engines, including the Stirling engine, cloth making, bicycles, etc. Today, they are used in automotive modules, roller coaster systems, medical devices, manufacturing machinery that requires precision and complex prosthesis. Next is the 4-bar mechanism analysis.
Thank you, Brooke. For our 4-bar mechanism analysis, we decided to make our 4-bar linkage a double rocker. The way we were able to define this mechanism is by using the equation L plus S is less than P plus Q. If this equation is true for our input, then it's a type 2 mechanism, which in our case it is, and type 2 mechanisms are all double rocker mechanisms. In our project description, we were given the link length for link 2 and link 3, and also the position of link 1. And we were told that our third link is to be the input value, along with the input position is also going to be the input velocity and acceleration. Our unknown values are the length for R1 and R4, along with their respective angular velocities and angular accelerations, along with the coupler position of S. For our position analysis, we had to solve for the positions of link 2 and link 4. After using complicated equations, we were able to optimize our selections to our link 1 being 20 centimeters and our link 4 being 65 centimeters. Both of these lengths gave us a range of 246 degrees for our theta 2 and theta 4 to move within. So for our velocity analysis, we're presenting to you a graph representing the angular velocity for link 2 versus our position of link 3. As you can see, we have a range of motion from 102 to 248, which is a range of 246 free degrees of motion. For our coupler position of S, we had to use an equation that is dependent on theta 3 and link length 2, along with a given beta value, which is the angle that our coupler position S is with respect to link 3, and also a link length between joint 2 and position S. So this graph describes the motion of position S while going through 360 degrees for link 3. A particular application for a 4-bar mechanism is a bicycle suspension system. What we want you to note here is that this would be our link 1, this is link 2, this is link 3, and this is link 4. And the motion that this suspension system will undergo is highlighted when this bicycle is either going over a bump or is abruptly stopping, because then this link 3 will go through a motion, and both link 4 and link 2 will do a rocker motion as expected. And this is an animation of our 4-bar link. Obviously this isn't the full 360 degrees that we analyze in our report, but for the specific application, we're simply using a cutout of the range, a specific range within the range that we analyze. So this is just, you should imagine that this is the bike doing an abrupt stop, then the suspension system is bringing it back to where it needs to be. And now I'm going to pass it over to Raheel.
Thank you, Kevin. For slider crank synthesis, we are given initial conditions from which we are to iterate and do mathematical processes to obtain a real-world example that we can apply it to. In our slider crank analysis, we were given these initial positions from which we were obtaining values, and if we didn't find those values reasonable or able to find a real-world example for, we were able to change them or iterate them by plus or minus 1 inch for each of them, while maintaining the link length or position length between position 1, 2, and 3 respectively. So the process we used first was to find the center point of A, go through the link length, and go to find the link length R2, which would be our crank arm, from position A's, all the position A's, find the pole positions, and from the pole positions find the circle of sides. And from when we find the circle of sides, we pick an arbitrary C value and calculate our XC and YC in a different coordinate plane in order to obtain our R3 value. But in order to obtain our R3 values, our C values have to be in line. So these are the points that we used after multiple iterations that worked with our example and what we found reasonable. As you can see here, for example, the first one went down -1 on both the A1 and B1 for both X and Y. So this is the C values that I spoke of before, and if they are not in line, then saying that's position 1 up there, 2 and 3, if they don't go in order and in line, we can't use it. So for our example, it works out perfectly. It's a straight line, and our least method of squares says we have 0.9987, which was expected because of rounding errors that could have occurred. So for our application, we had a displacement of 12.92 inches from a crank arm that was 6.19 inches and a linear link that was connected to a slider of 19.27 inches. So the application we chose for this slider crank mechanism can be used in a coin dozer game that's seen in casinos and arcades. The mechanism consists of a sliding platform that displaces a short distance. Okay, so this is the first iteration of our coin dozer pinball machine hybrid. Because of our link length arm being a little oversized, 19 inches to be exact, we had to create this hybrid between the two machines. Our displacement is 12 inches, so as you can see, the slider goes to the front, to the back to push the coins a minimal distance in order to maintain the game, and that is coin dozer. Here's a closer up mechanism, how the mechanism works. The crank arm goes around, pushes the slider, comes back, and goes forward again. Again, this is the first iteration. And here's Brooke to conclude.
So what we learned is the importance of analyzing the slider crank as well as the 4-bar systems, because we are using this design to further create new machines and get more sophisticated. And it's a really good way to analyze a system to see what your design will turn out to be. So what we would do better in the future is we would use a program that's capable of doing multiple iterations at a faster pace than what we were able to do through Excel, as well as better simulation software using a newer version of SolidWorks in order to see the slider crank analysis better, as well as the coupler motion better for the 4-bar analysis. So it was definitely a collaborative environment. Kevin did the 4-bar analysis, Raheel did the slider crank synthesis, and I stepped in and oversaw the calculations just to verify that everything was done accurate and for a second set of eyes looking at it. And in the end, we all collaborated together in order to complete the SolidWorks analysis and the animations as well. And I created the report in the end. Thank you, we're Team 3.